Welcome back to another CHEM271 tutorial. This will be a shorter tutorial, just quickly going over 5 mechanisms from glycolysis that I did not go over in my previous glycolysis video. So the first one we will look at is for phosphoglucose isomerase. This is responsible for the conversion of glucose 6-phosphate into fructose 6-phosphate. So starting over here with glucose 6-phosphate, this all involves a basic amino acid, which in this case is glutamate. Glutamate is acidic, but it can also act as a base, as it is doing here. Okay, so what is first going to happen is this basic glutamate is going to come and grab this proton off of carbon 2 in glucose 6-phosphate. The electrons in this bond will go and form a double bond here, and then the electrons in the carbonyl will go up to an oxygen, and then an H plus will come in and turn the oxygen into an OH, so turn the carbonyl into an OH, and then we get a double bond. This here is called an anidyl. So the anidyl, in this case, this is a cis anidyl. Basically, it's a carbon double bond there, CC double bond, with an OH on each carbon on the same side, and in this case we have an H and then an R, but just like more generally you just have an R on both. Okay, so that's what an anidyl group looks like. So we have an anidyl intermediate here, and then what happens is general acid catalysis. So essentially what's going to happen is this the electrons here in the OH bond are going to come, reform the double bond, or form a double bond here between the carbon and the oxygen, so make a carbonyl on carbon 2, and then the electrons in the double bond here are going to come and take the hydrogen from the basic amino acid. So essentially this is acting as a general acid because it is giving up the proton, and the carbon double bond here is our nucleophile. Okay, and then another H comes in to give this carbon up here another H. So now we have successfully moved the carbonyl down from carbon 1 to carbon 2. So that is how glucose 6P gets turned into fructose 6P, right? All right, this is definitely the most complicated mechanism of glycolysis that is in the slides. So this is the mechanism of aldolase, which converts fructose 1,6-bisphosphate to glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. Okay, so essentially we have these 4 amino acids here. We have a lysine, we have a basic amino acid, acidic amino acid. Okay, and this is the active site. So here we have fructose 1,6-bisphosphate in the active site. So the first thing that's going to happen is the formation of this right here. So this is referred to as a Schiff base. Okay, so the first thing we're going to do is form that Schiff base. So what's going to happen is the lysine is going to attack the carbonyl, okay, and then the electrons from the carbonyl are going to come and deprotonate the acid, like so. Okay, and then that is going to reduce the carbonyl to an OH, okay? And we're also going to form a bond between the fructose 1,6-bisphosphate and the lysine, okay? So the next thing to do in order to make the Schiff base is, so this basic residue here is going to come and it's going to take that proton off the nitrogen in the lysine. So this nitrogen here has a positive charge. There's another bond here. And then these electrons here are going to go and form a double bond between the nitrogen and the carbon. And then the electrons in this OH are going to leave and form water. So basically an H plus is going to come in, the OH is going to leave and combine with this H plus to make water here, okay? So this is how the Schiff base is formed. So steps 1 and step 2 are to form the Schiff base. The reason why we can't do this with glucose and why we have to do this with fructose is because we need the carbonyl on carbon 2 in order to form this Schiff base. So you need the carbonyl on carbon 2 to make a Schiff base. The carbonyl on carbon 2 only exists in fructose. It does not exist in glucose. Thus, this reaction cannot happen with glucose. Okay? And this is all general acid-base catalysis, as per usual. So the next thing that happens is this reaction, which this is called an aldol cleavage. Okay. So, and this will result in the release of the glyceraldehyde 3-phosphate. So the arrow pushing for this is as such. So assuming the marker doesn't die, the basic residue here is going to come, it's going to attack the proton here, and then this is going to reform this carbonyl here, okay? And then these electrons then have to go somewhere because this carbon now has 5 bonds. So where are they going to go? They're going to go here and form a double bond here and this between these two carbons, okay? So between this carbon 2 and carbon 3, these electrons are going to form a double bond, and then that means this carbon now has too many bonds. So the electrons in this carbon-nitrogen double bond then go back to the nitrogen, okay? So that's a lot of arrow pushing. The result of that is we have broken this bond here and we have formed a carbonyl, making an aldehyde. So glyceraldehyde is released, right? It's an aldehyde. This is carbon 4, 5, and 6 of fructose 1,6-bisphosphate. It's an aldol cleavage. And what we're left with is in the active site is these 3 carbons still bound to the nitrogen, but now we have a double bond between these 2 carbons here. Okay? So now what we have to do is we've gotten rid of the glyceraldehyde 3-phosphate. Now we need to make the dihydroxyacetone phosphate. So in order to do that, the next thing that happens, there's a lone pair here on this nitrogen, and this lone pair is going to reform this double bond again. And then this double bond here is going to be broken, and it is going to come down here and remove this hydrogen from this basic amino acid. These electrons here will go to the basic residue. And then the result of that is we have reformed the Schiff base, and now we have the OH on that last carbon, which we see in dihydroxyacetone phosphate here. So the last steps of this are really just the reverse of what we've seen here. So what we've seen going in this direction is Schiff base formation. So now the next set of steps are to get rid of the Schiff base. They are literally just the reverse of these. The mechanism for that is not shown in your slides, but it's really just the reverse of this. So what happens is Schiff base hydrolysis. This marker does not work. Schiff base hydrolysis. Okay, Schiff base hydrolysis. So a series of steps happens, and then this is removed, and what's left here on this carbon is a carbonyl. So notice how we start with the carbonyl on carbon 2, and the nitrogen attacks that. We end up with the carbonyl on carbon 2 as well after that cleavage, okay? So what we end up seeing is that this is carbon 4, 5, and 6 in G3P, and carbon 1, 2, and 3 in DHAP, and those correspond to the carbons in fructose 1,6-bis-P. All right, so that's definitely the most complex mechanism. Let's look at another one that is not this complex, all right? All right, now looking at Triose Phosphate Isomerase. This converts DHAP back to G3P so that you have 2 G3P entering the payoff phase of glycolysis. So here we have a glutamate and a histidine in the active site, and here's DHAP. So the first thing that's going to happen is this carboxylic acid from glutamate is going to attack one of the protons, and then this is going to form a carbon-carbon double bond here. And then this will, again, cause the electrons in this carbonyl to come and take a hydrogen from the histidine. Okay? Then what we're left with is, you might recognize this again, this is a cis anidyl. Okay, so same as what we saw with phosphoglucose isomerase. Okay, so now we have this double bond. It's cis because we have the OHs on the same side. And now what's going to happen is this histidine, now that has a negative charge, is going to come and take an H from carbon 1 instead of from carbon 2. So it's going to take it from carbon 1, and then this will form the carbonyl here, and then, or no, it won't form the carbonyl yet. So these are actually going to, in this step, it's just going to go to the oxygen. It'll form a carbonyl in the next step. I don't know why this is 2 steps, but all right, so now essentially we've just given this oxygen a negative charge. We've reprotonated the histidine. So now we have to get rid of this carbon-carbon double bond here and reform this carbonyl. So the mechanism for this, the negative charge comes down, reforms the carbonyl. The double bond will come and take the proton from the carboxylic acid, give the electrons back to that. Now we've reformed our histidine and our carboxylic acid from the glutamate and have moved the carbonyl up to carbon 1, remaking glyceraldehyde. We've remade the aldehyde. So basically we've just converted the ketone, which has the carbonyl on carbon 2, to an aldehyde, carbonyl on carbon 1. All right, that is the mechanism for that. So next we will look at glyceraldehyde 3-phosphate dehydrogenase. All right. Glyceraldehyde 3-phosphate dehydrogenase. This enzyme converts glyceraldehyde 3-phosphate to 1,3-bis-phosphoglycerate. So, starting out here with glyceraldehyde 3-phosphate, I have abbreviated most of the compound as just an R group. All that's shown here mainly is just the aldehyde. So we have a cysteine residue here and a histidine, and we also have an NAD+. The NAD+ is actually important in the mechanism. So the first thing that will happen is the sulfur here will come and attack the carbonyl. Okay. That's the only arrow you need to show for that part of the mechanism. And then what's going to happen is you're going to have this intermediate here, so a carbon, hydrogen, an OH. So yeah, I think you can show that too. And an R group. So this is called a thiohemiacetal. Okay, a thiohemiacetal. It's not, the marker isn't working very well, but so thiohemiacetal, so it's a carbon, it's sp3, and it has a sulfur on it. Okay, and then what is going to happen next is the histidine is going to attack the proton. This is going to reform the carbonyl, and now it has to kick out something, and what it's going to kick out is actually the hydrogen, which is going to be used to protonate the NAD+. Okay? And then this will form a thioester. So remember, the thioester is high in energy. And then what's going to happen next is there's no more no more arrow pushing here. Essentially, the NADH is going to leave, a new NAD+ is going to come in, and a phosphate is added. So this sulfur carbon bond breaks, and a phosphate group is added on instead. The NAD+ is still there. So the NAD+ here is important in this last part because, oh my goodness, this marker's bad. There we go. NAD+ stabilizes the introduction of the phosphate group. Okay, so that is why the NAD+ is here, because it makes it so that this phosphate is more stable. You have a positive charge next to a negative charge there. The last thing to note here is that this thioester is high in energy, as I've been saying. So essentially, why does this not form this sort of ester intermediate? Why does it form a thioester? It's because the ester is a lot more stable. So this is the sulfur intermediate. This is the so this is the thiohemiacetal, and this is sort of part of the phosphate intermediate, right? So these are both pretty high in energy, but if it forms an ester here, the ester is quite stable, so that means in order to get to the next intermediate in this part of the mechanism, it would need a whole lot of input of activation energy. However, because the thioester is also pretty unstable, it means that it's a lot closer in energy to the final product and to the intermediate in between, so it's a lot closer in energy to this unstable mixed anhydride here. So by having an unstable intermediate in the middle of the mechanism, it means less energy is needed in order to sort of get from starting material to final product, versus here where you have this huge dip in energy where you have a very stable intermediate that will be difficult to turn into the final product, which is the very unstable mixed anhydride. I need to get better markers. Okay, so that is it for this mechanism. One more mechanism. All right, last mechanism, phosphoglycerate mutase. So this is turning 3-phosphoglycerate into 2-phosphoglycerate. So we're starting out with 3-phosphoglycerate, and I forgot to write it, this is 2-phosphoglycerate. All right, so here what we have is a histidine with a phosphate group on it and a histidine without a phosphate group. So essentially we're trying to get this phosphate to move up here, or actually we're going to have this phosphate move here, and then this phosphate is going to go back to the histidine. Okay, so the first thing that's going to happen is this histidine is going to act as a general base. It's going to pick up this proton, and then the electrons in this bond are actually going to come and steal this phosphorus, this phosphate from the histidine. And this histidine is the PO3 - 2 donor. Okay, so and then the electrons here can go back and go to the nitrogen. Okay, so now what we've done is we've put the phosphate on both carbon 2 and carbon 3. So now we need to get it off carbon 3. So in order to do that, this nitrogen here, so this is going to now act as a PO3 - 2 acceptor, and this will act as a general acid, which means that this is going to be a proton donor. Okay, so now what will happen is this will come and it will steal the phosphate from carbon 3, and then the electrons in this bond will come and take the hydrogen from the histidine, which acts as a general acid because it is losing a proton, it is giving it up. And then what you get is 2-phosphoglycerate, and you've restored the phosphate donor histidine here and just the regular histidine here so that it can catalyze another reaction. So that is it. Those are the 5 mechanisms for glycolysis that you have to know. Thank you.